that what we have given last week, right? Which to me is very important because you know most of the semiconductor devices they need the electrode, right? Because the devices are mostly turned on by electrical currents. If the unit turn on either by voltage and then currents, you need metal to conduct the currents going from the battery or the voltage source to the active region of the device, right? So how do you choose the right metal in order to maximize the injection currents, which will give you a big difference, right? Because we can have two types of metal semiconductor interface. So if you want to maximize the injecting the currents from the metal to the semiconductor, which contact should you choose? You have two choice, right? One is to form the Omi contact, the other one is to form the Schottky contact. Which one can give you the maximized currents? Schottky, Omi. Omi, yes. So see, this is the band diagram for the N-type Omi contact, right? If you choose the Omi contact, you will have a less potential barrier, right? So this is metal, this is semiconductor. At the interface, the electron is traveling above the Fermi level or inside the conduction band, right? So you can see when the electrons are injected from the metal to the semiconductor, you need to go through the interface barrier. So this interface barrier, if it is smaller, you can have a larger currents, right? For the Schottky contact, which is on the left side, you can see there is a Schottky barrier because the band is bending up. So this will impede or block the currents flowing from the metal to the semiconductor, right? So you need to choose the metal with the smaller Wolf function, right? So I told you, you have three key parameters to memorize. Make sure you understand the three key parameters. The first one is Wolf function, right? You need to know what's the definition of Wolf function, right? Which is the energy difference between the Fermi level to the vacuum level. You need to know what we mean by vacuum level, right? That's the spatial reference energy level in semiconductor band diagram. That's the minimum energy level for the electron to be free from any material, right? It's like you shoot a rocket from the Earth to the outer space, free from the gravity of the Earth, right? Second one, you need to know what is the electron affinity. I make sure you understand the definition of the electron affinity, which is the energy difference between the conduction band and the vacuum level, right? Because you need this value, electron affinity, to calculate Schottky barrier. Right? Schottky barrier is given with the equation shown above, right? So the chi is the electron affinity, right? Last one, you need to know the equation for the Schottky barrier because this is the important parameters for you to estimate the turn-on voltage of your Schottky contact because it is behave like a peer junction, right? So the IV curve of a peer junction and IV curve of a Schottky barrier is very similar, as you can see from the class notes. This is the IV curve of the Schottky barrier. And we also have a turn-on voltage. This is the turn-on voltage, which is the turning point from very small current to exponentially increase the current. So the turning point is determined by the Schottky barrier. Okay, three key parameters. Make sure you know the definition and the equation. Wolf function, electron affinity, and the Schottky barrier. Okay? 知道哦。 期末考一下考 you will see this again in the final. Okay? I just realized even I told you a lot of the questions to be appeared in the exam, you still don't do well. Okay, so I plan to give you more equations, more questions in the final. Okay, to help you have a better grades. 知道吗？我发现我期中考写的题还不够，平均只有57分而已，比之前还要少。之前大概都65到70之间。那是怎样？考太难了，还是写题写太少？没有超过80分的 ，so strange. Nobody is above it. In the past few years, usually I have about 5 students who has the grades above 90, and 10 maybe around 80 something. Right? But this year, I see no one with the grades above 80, which is strange. Okay? Maybe I have the question too hard. I don't know. Okay. Alright, so this is the work function of many different metal. Okay, so it's like a band gap of a semiconductor, which is a fixed value. So before you choose the metal for the contactor, the first thing you know is to make sure you are achieving the ohmic contact or Sharpey contact, because that's the results of the work function. If you choose the wrong work function, you will have the wrong contact, right? So each of the value is showing the work function, right? So usually the work function above 5 is large work function. Work function below 5 is considered small work function, right? So those in red box, right? Gold, aluminum, nickel, palladium, platinum, titanium. The six metals in the red box are the common metals for you to form the electrons. Okay, so you know the typical high work function is given by gold, palladium, and PT, right? So usually the expensive metal have high work function. Cheap metal has low work function. Cheap metal is what? Aluminum is cheap, right? So aluminum is how much? Around 4 to 4.2. Okay. And for the size of on the side of a semiconductor, usually you will have some very special phenomena, which is called Fermi pinning. Okay, Fermi level pinning, right? For example, it doesn't happen to all semiconductor, but for some special semiconductor like indium arsenide or gallium arsenide, you will find the Fermi level at the surface of the semiconductor is a fixed value. If this happens, it doesn't matter which metal you choose. It always gives you a certain type of ohmic contact. It's like this case, metal and N-type of gallium arsenide. You usually have Sharpey barrier because the bending is always going up due to the presence of a surface defect or the interface state. So usually on the surface of a semiconductor, you will have a lot of impurities. Impurities is the result of the interaction between air and your semiconductor atoms. Right? So usually the surface structure or the chemical structure, chemical states, physical states is very complicated. You have all kinds of impurities from the air, and then once the impurity is fixed on the surface, you have no way to change the Fermi level. OK？ 所以在半导体的表面通常会有很多高浓度的电子，或是表面的缺陷。这些高浓度的电子或是缺陷会有高浓度的电荷，不管是动的会动还是不会动的，所以就会让它的这个 Fermi level 固定在一个位置，这个位置就会让你无论是选什么金属，公函数大的还是公函数小的，永远都是 shocking barrier， 或是永远都是 ohmic contact。像这个就是 N-type 的 shocking barrier。This is the N-type ohmic contact. One is bending up, one is bending down. Regardless of the metal you choose, this is the special case for semiconductor, which is very important. You want to know this, otherwise you will see some strange behavior, which is the IV curve is always shaky or ohmic, no matter what kinds of material you choose, what kind of metal you choose, because that's the result of Fermi level pinning due to the high density of the surface states. Okay? So if you look at the schematic of atomic structure, right? So usually on the surface of a semiconductor, you have a lot of dangling bonds, which is the incomplete chemical bonding, right? So in normal case, deep inside the bulk of the semiconductor, usually you have the covalent bond formed between two adjacent atoms, right? But on the top layer of the atom, because you have nothing above the surface, so usually the valence electrons is not forming the covalent bonds with any atoms. And in this case, this reactive valence electrons is highly to react with the impurities inside the air, which will result in high density of the surface states or high charge density on the surface. This is the reason for you to have a surface pinning. 所以半导体的表面通常是一个很复杂的环境。为什么？因为它表面有很多没有完成的共价键，我们叫它是选键，就是悬在半空中的这个价电子。这个价电子很容易跟空气里面的杂质反应。It's like a very reactive free electrons, which can have oxidation, reduction, 氧化或是还原。And after the oxidation or reduction process, you will have all kinds of different surface structures, surface atoms, surface defects or impurities, which will make the Fermi level unchangeable. Okay. So Fermi level is very sensitive to the concentration of the electron. So once the electron change the density on a certain position, surface, the Fermi level in that area is not controllable. Okay. 所以只要有一个地方有高浓度的电子或者是电荷，正电荷或是负电荷，那个地方的Fermi level通常就会很难被改变，因为Fermi level的位置就是反映出这个电子浓度的这个结果。Okay. Right. So that's the difference between theoretical equation and the reality. So this is the reality. Fermi level pinning is the reality. Questions? If no questions, we will move on to the device part, which is the transistor. Okay? So here is a brief history of a transistor. You know, before 1947, before 1947, you don't have the word transistor. This is a new word, 一个新的字。 curve. 1947. Before that, you only have a vacuum tube, okay, which give you the IV curve going like this. Okay, it's not a straight line, but give you some curvature with a certain slope, right? And some scientists in the Bell Lab in the US, 贝尔实验室 one of the scientists, he want to do something special, okay? He want to see if it is possible to make something, with controllable resistance, okay? So this is the ideal device in trying to make. This is the voltage, and usually you can only have a resistance, right? If it is a resistance, the IV curve will go like this. Right? But if this resistance is controllable, you can have more combination of circuit design or application, right? So if you try to build something with control the ball resistance, right? So they invent a new word, combining transfer plus resistor. Transfer resistor, so they make it transistor. Okay, that's the new word after 1947, right? So you can see the basic difference between a resistor and a diode. Right, so this is a diode, not a transistor. Okay, because for a diode, I is equal to I 0 times KT QV minus 1, right? That's the equation we derived before the midterm, right? This is the device of the components with the resistance not changeable, right? Here, R is not a constant, right? Constant. Here, I is a constant. This is not the scientist need because the R is not easily controlled. But not easily controlled. What do you mean by easily controlled? It means the slope of this IV curve is fixed at a certain range of voltage, not change all the time. It cannot be too sensitive, otherwise your circuit will not be stable. It got to be changeable, but in a stable way. 它是可以控 控制的，可是不能太敏感。这个就太敏感，因为它每一段的斜率都不一样，斜率就是它的电阻，对不对？斜率就是 I 跟 V 的 ratio， 对不对 ？Okay, so this is not the ideal transistor. Okay, ideal transistor will give you the IV curve like this. Okay, how do you use it? For transistor. V, I, X. You have many different lines, right? Okay? And in the operation zone, for example, here, you will be in 1, 2, 3, 4. You have 4 working points, right? Each working point will give you a certain current. I1, I2, I3, I4, and it will give you a certain resistance. R3, R2, R1, right? Because R1 is equal to V in divided by I1, right? You have the same input voltage, but different output currents, which can be easily controlled by a third terminal, V in. How do I say? V from 1, V from 2, V from 3, V from 4. Okay? So you don't have only 2 terminals, you have 3 terminals. So the third terminal is to control the resistance. Okay? So this is the ideal case of a transistor, which can make you easily control the resistance running through the device, right? So if you slightly change the value of V in, larger or smaller, you don't change much the current, which will give you stable resistance at a certain input condition. So for this one, R is not a constant. Not a constant, right? It can be R1, R2, R3, R4. And very easy control. You can change the voltage applied to the third terminal and then give you a very different but stable resistance. What do you mean by stable? Stable means even you change a little bit of the V in, apply it to the device, because this IV curve is flat after a certain voltage. It doesn't change much the output currents, right? So this straight line, this flat line, saturation zone, is the key to provide a stable output current. This is the stable output current. You don't like the currents go like this. This is not ideal. Okay. Okay. Ideal one is like this. Horizontal, no change of the current. This is not change. This is not stable. This is stable. 大家知道哈，当我输入的电压大于一个门槛的时候 ，threshold voltage. So this is more like a VTH, which is the threshold voltage. Once your input voltage becomes larger than the threshold value, your output current is stable, which means it does not change with the input voltage. In that case, you can have a very stable resistance once you fix the terminal voltage, right? So that's the very basic idea of a transistor. You have to produce a device or component with controllable resistance, okay? Controllable means easily change and stable. 它很容易改变，可是又很稳定。一旦改变之后，不可以变来变去。Although this is also a controllable resistance, but not stable because the slope of this line is not constant. A little bit change of the input voltage will give you bigger change of the resistance, right? So, not an ideal transistor. This is an ideal transistor, right? So this is why you see at least 3 lines. Usually you see more than 5 lines corresponding to 5 terminal voltage, right? So that's the basic operation, basic purpose of a transistor. It got to be a device with transfer resistance. Okay? Before the invention of this transistor, you need a vacuum tube to do the same thing. You can also make a transistor, but not by semiconductor, but by vacuum tube. So what's the issues of a vacuum tube? 真空管. Issues is it is so big. One vacuum tube, one transistor, very old type, right? So if you want to build the computer with vacuum tube, you need a whole room. Okay, maybe larger than this room to do simple algebra. Okay? Nowadays, because of the advance of the semiconductor fabrication, you can squeeze so many transistors inside a small area, right? So that's the latest version invented by NVIDIA last year, 2025. How many transistors inside is 2.7 by 2.7 square centimeters? How much? How many? 208 billion. 208个 billion 是几啊？208 billion transistor inside this area, less than your hand. OK， 比你的手掌还要小。OK，2000亿个电晶体，全部都给你挤在一个晶片里面。OK，so you can see each transistor only have the gate length of how short? 5 nanometer. Okay, that's the power of TSMC. Because TSMC nowadays is the only one company in this world being able to produce such a small transistor with high production yield, making it profitable. Intel, Samsung can also do 5 nanometer process. The problem is that the production yield is so low, you cannot make a profit. It's another story to make the mass production, not by demonstration. OK， 做1颗可以，可是做100万颗的晶片，良率都要很高才能赚钱。OK， 就是台积电目前大家一直追捧的原因，因为它有办法用可以赚钱的方式量产这种耐冷电晶体。三星、Intel 也可以，可是它没有办法有这么高的良率。OK， so this is a big change in how many years? In about 75 years. Okay, less than 100. You have a so big change. Okay? So that's the first transistor invented in this world. then the size of the gate length is not a gate, it's not the field effect transistor, it is a BJT, bipolar junction transistor. So the dimension of the critical gate or the base area is 50 million nanometer. Okay? Nowadays we can do 732 nanometer. So this is 15 million, 5000个纳米，5000万纳米 ，OK 的制程。世界上历史上第一颗电力电是5000万纳米制程。Okay, you can see the magnetic eyes. Do you know the key components? Right? How many wires do you see on this picture? Okay, 1, 2, 3, 4, 4 wires, right? So here is the label of the transistor components. Okay, you have emitter on the left hand side, collector on the right hand side. Actually, the triangle is nothing but a plastic material. 只是一块塑胶而已. That's not the key material, okay? On the edge of that triangle, you have gold or some metal to make a contact. So it's also not special. Plastic is an insulator. Metal is a conductor. So that's nothing, okay? Key components in this first transistor is germanium. That's the key breakthrough. Before germanium, the scientists in Bell Lab they tried silicon, but the silicon does not give you the ideal Ivy curve. You know what's the issue? Although we have a silicon to make the transistor, but in the first invention of the transistor, silicon is not a good material. They try silicon but fail so many times. They cannot produce a controllable resistance until they change the material from silicon to germanium. Do you know what's the difference? Although both of them are semiconductor. The problem of silicon is that silicon easily oxidized with air. So it's not a pure silicon on the surface. Okay, once you have a thin layer of silicon dioxide on the surface, that thin layer, SiO2, is an insulator. Insulator make the resistance very difficult to change, right? So there's no easy way 70 years ago to remove that thin layer of SiO2, because once you expose the silicon semiconductor to the air, it will oxidize in 1 minute. After that minute, you have a thin layer, a few nanometers of the silicon dioxide cover up the whole surface of the silicon semiconductor, make it basically like an insulator. And then the scientists change the material to germanium, which is less oxidized. Okay, it takes so many years to realize such behavior. Okay. Do you know which one is the key to replace the transistor using silicon to germanium? Jacques-Bardeen. Okay, because they have 3 scientists elected working together to produce the first transistor in human history. Jacques-Bardeen and William Shockley. Shockley is the name we have during the Ivy curve derivation. Shockley approximation, which is the boss. Jacques-Bardeen is the new engineer, and the other one is Braden. Actually, Jacques-Bardeen is a theory scientist. He is the only one who have studied quantum mechanics, so he knows the behavior of electrons is different on the surface of the semiconductor than the behavior of an electron inside the semiconductor. So you realize the oxide layer on the semiconductor of silicon is the killer for the transistor. Okay, unless you make it thin enough to have some turn-on effect. Okay, so anyway, that's the first transistor, which is the BJT, bipolar junction transistor. Okay, so that's the schematic show you how the transistor is working. Inside the germanium, you have a top layer of a hole, which is p-type. Bottom layer is n-type. You have a high concentration of electron, right? So when you apply the voltage between the top and the bottom, see in the bottom you have a metal base, right? So this is the base. Okay, and the contact point, which is the tip of the triangle, is the key for you to change the resistance by applying the potential between the top of the triangle and the metal base. So you change the resistance by different bias values between the plastic wedge of the triangle and the bottom metal base. 所以关键就是在这个三角形的塑胶块跟这个germanium的接触点。Okay, the key structure is the contact point between the triangle tip on the germanium surface. That contact area is the region with different resistance changed by the bias applied. Okay, between the top and the bottom. So this current is produced by emitter and the collector. So the current is running from emitter to the collector, but resistance is controlled by the base currents. Right? This current is the current flow into the middle layer, which is the contact point of the triangle. 这样知道哈，这个是基本的运作原理。OK。So nowadays we have two types of transistor. The most common one is the field effect transistor. In short, we call it a FET, right? Field effect transistor, right? Because this FET is using electrical field to control the currents of the IV curve. So you can see you have the gate voltage, which is to produce voltage from 0 voltage minus 0.1, minus 0.3, 0.5, minus 0.7. So this value is the value of voltage. But for BJT, it's not controlled by voltage. The IV curve for all the resistance is controlled by currents. So you can see this is the base current of 60 microamp. So the unit is different. One is voltage, one is ampere, right? So which one is more popular now? FET or BJT? FET, right, is more popular, but you still have some device using BJT as the transistor because of some consideration, right? So the current you see here along the blue line is the current flowing between the source and the drain, right? And the conductance between source and the drain is controlled by the gate voltage on the top, right? So you can apply different bias to the gate and change the resistance or conductance between the source and the drain. So you can have a different ratio of different currents, right? So you have a two region. One is called the saturation region, where you have flat electrons currents, flat electron currents. This is the linear region, right? So in the operation area of a transistor, it is working in this saturation region because this region gives you stable currents for a wide range of voltage change. You don't have to work the device here because give you not stable currents. Not good. You got to have a stable current in this region. Stable current in this region. Okay? So we call it an active region. The region for the transistor to be used. Okay? So for the BJT, you change the currents between emitter and collector by applying different currents from the base, which is the layer in the middle, okay, in between the emitter and the collector, right? So you can have some different performance of the transistor. Let me see, I thought we have some comparison. Okay, the key advantage of a FET is high speed. You can turn it on and off with the field effect faster than by the current effect. Okay, so this one will give you high speed response. Okay, on and off, right? And this one is saving more power. Okay, you can save more power and make it smaller, right? But the key issues of a field effect is cost, because it takes a lot of money to make it small. Okay, so this one is faster but more expensive. This one is cheaper, okay, but slower in response. Okay. So you can check the GPT or AI model to list the advantage and the disadvantage between FET and the BJT. But the key difference is the high frequency response and the device size. You can make the FET very small. So the TSMC 3 nanometer, 5 nanometer, even 2 nanometer, they are all FET. BJT is usually much larger now using nowadays technology. 所以说做的国内3年的都是长效电晶体。这个 BJT 就是bipolar的都是比较大。Okay. Right. So we just give you a short. Easy introduction. Now we need to go into the theory. Again, like we do with PN junction, we firstly give you qualitative explanation, okay, without giving you any equation. Just give you the physical story, how it is in operation, what's the physical status before the MOSFET is turning on and off. Okay, so here we can see two states. Okay, so on the top you have the FET, almost FET in the off state, which means you have a zero bias applied to the device. Okay, you have 3 terminals, right? Source, gate, and the drain. Okay, with zero bias, right? And after the device is entering the saturation region, you have the bias applied to the gate, which is in the middle, and the drain. Okay, so this is the corresponding band diagram for the MOSFET in operation. That one is the corresponding band diagram for the MOSFET in off state, which means you have a zero current here, right? So for the device to be turned on, you need to go through 2 stages. The first stage is to induce a channel. A channel is the conductive path between the source and the drain. So you can see on the top, you have a P-type of substrates, okay? And the source and the drain is connected to the N plus region. So between the N plus region, you have a P-type, which is showing no channel, okay? Channel is the conductive path between the source and the drain, right? So once you have the channel induced, then you need to increase the voltage and the drain more and more, right? Until you reach the saturation region. So when you reach the saturation region, that means your device is in operation. In this state, your N diagram is going like this, all the channel distribution is like this. You can see the shaded area is the channel or the N plus region. Once your device, your MOSFET is into the saturation point, your channel is cut off. What do you mean by cut off? That means it's not continued anymore between the source and drain, only extended to this point. Beyond it, you have a zero channel. Okay. Still, you have some finite currents. Okay, so that's the two steps. First step, to induce a channel, to make it conductive between source and drain, so that you can flow the current between the two terminals. And then you need to keep increasing the channel diode or channel voltage. You need to keep increasing the drain voltage, right? Yeah, that's the channel. Okay. So in total, you will have 6 band diagram to draw. Okay. The first 3 is to induce the channel. The last 3 from 4, 5, 6 is to induce the saturation currents. Okay. So you can see the key step in the channel induction. 你要诱发一个 channel 的通道 ，OK？ So you can see step 1, where you have a no voltage applied to the 3 terminals, okay? And step 2, you slightly increase the gate voltage. See the difference between 1 and 2, right? In the 1, 0 voltage for the gate, 0 voltage for the drain, and the source is grounded, right? That's your initial situation, okay? So you know, in the drawing, I show you the depletion region. I hope you can understand everything in these slides, okay? Because the operation of a transistor is not easy to understand. Okay, if you are learning this for the first time, it's a big headache. Okay, so I will try to be slow. Okay. Oxide. So we are talking about the oxide layer. We are talking about the MOSFET, which is short for metal oxide transistor. Okay. Metal oxide semiconductor. So this is P-type semiconductor. This is the depletion region, 空乏区. Okay, this is the N plus region, where you have a heavily doped donor incorporated into this N plus region. Alright? So you have a PN junction in the blue region, PN junction in the blue region, PN junction, PN junction. Okay, so we will continue the talk after the break.